So P10.2, weight and terminal velocity, and this is a really good example of how force is linked to acceleration and how as your force changes, your acceleration changes, and the effect that this has on your velocity. So if we take a look at what weight actually is to start with, so we'd say that weight, which is measured in newtons, so that's the force aspect of it, is equal to your mass in kilograms times by the gravitational field strength, which we call G. Which you can assume to be 10 unless you're told otherwise. So weight equals mass times gravitational field strength, which we can assume to be G, and the units for gravitational field strength are newtons per kilogram. And you can see that that must have been the case, because if you divide weight by mass, then you get the gravitational field strength. Okay, so that's the force that's pulling us downwards. Not the mass that's pulling us downwards, not gravity that's pulling us downwards, it's weight that's pulling us downwards. That's the force, and it's the combination of mass and gravitational field strength. So let's have a look at what happens when you fall. So to start with, let's use the example of being on the moon, okay? Because on the moon there is gravity, but there is no air resistance. So if I drop a feather on the moon, then the force that's acting on my feather is just the weight. I don't have anything else acting on it at all. It is just the mass of the feather times by the gravitational field strength of the moon. And then if I look, and then if you remember from last lesson, we said that force equals mass times acceleration. And remember that this force is the resultant force. Okay, then we know that the acceleration, that this feather must be accelerating, because we know it's got a resultant force, and that resultant force is the weight of the feather. So let's put. So if we know that the weight is provided force, then what we can do is we can say that mass times gravitational field strength is equal to mass times acceleration. And if I put that into symbols now, just so that I don't have to write it out every time, it's going to be mg equals ma. And this is the mass of the feather, so this cancels out. So what I can say is I can say that the acceleration on that feather is equal to the gravitational field strength of the moon. Because all of the force, all of that resultant force is all being provided by the weight. And weight is mass times gravity. And that's why, if I was also to drop a hammer on the moon, even though the value for its weight is much bigger, it would now just be the mass of the hammer. So that's the mass of the feather times gravitational field strength equals the mass of the feather times acceleration. So the mass of the hammer times gravitational field strength equals the mass of the hammer times by the acceleration. Well, it doesn't matter what that mass is, it still cancels. And that's because of Newton's second law. It's saying that how hard it is to accelerate depends on your mass. But if you don't have air resistance, the only thing that's causing you to accelerate is your mass. So those two effects cancel each other out. Which is why, on the moon, if you were to drop a hammer and a feather, they'll both land at the same time. On Earth, that is a little bit different, okay? But first, what I just want to show you is I just want to show you what the graph of that would look like on the moon, okay? So this one is the velocity time graph and the distance time graph of this example where there is no air resistance. Okay, so let's do the displacement time graph first. Now, we know that it is accelerating because it's got a unbalanced force on it, making it go downwards, which means that the rate at which it goes downwards is going to be increasing. So, I'm going to have a graph that looks like this. And if you look at the tangent of that, you can see that my gradient is getting steeper and steeper and steeper and steeper and steeper and steeper and steeper. And on this example, you can see that the tangent to this curve is getting greater. Okay, the gradient of that tangent is getting greater. But the key thing is that it's a negative gradient, and that just tells you that it's falling downwards. So, because it's a displacement time graph. And then if I wanted to do the velocity time graph, then it's going to be instead of doing velocity time graph, let's do a speed time graph. And the reason why I wanted a speed time graph is because I don't want it to be negative. I want to show you. Oh, sorry. Terribly wrong. And that's the mistake that everyone makes. The acceleration is constant and it equals g. Okay, so the gradient here will equal the gravitational field strength of this one. Okay, because we know that the acceleration is g, and we know that the gradient is the acceleration on a speed time graph. Okay, if I'd have done velocity, then the graph would have had to have looked something like that. So that would have been the one for the velocity time graph, where you're getting more and more negative speeds. But I thought that was a bit, because when you drop it, it's going downwards. Downwards is always considered to be in the negative direction. So that would be if it was a velocity time graph, but I think it was a speed time graph just to keep it on the positive. So you're getting more and more negative going that way. Okay, so that's the effect without air resistance on the moon. Let's see how that changes if we add in air resistance. So, got a ball. You drop it. I've got weight. Now, I've also, to start with, when it's not moving, that's all I've got. But if I was then to look a little bit later, you'll see that I've now got a small bit of air resistance. Now that I've started to move, I've got a small bit of air resistance. And as I go faster, I've got a larger amount of air resistance until I reach what's called terminal velocity. And when I reach terminal velocity, the air resistance is exactly the same as the weight. So the way to look at this is if you look at what the resultant force is here, so let's say that was 100. Well, in each one of my balls, that 100 is not going to change because the ball does not get any heavier as it's falling. So that is 100 newtons in every single example. Which means that, so my resultant force here is going to be 100 minus the air resistance, which is 0. So my resultant force is 100 newtons. On this one, my resultant force is going to be, let's call that 10 newtons. Let's call that 50. call that 100. So that one is going to be 100 minus 10, so that equals 90 newtons. This one is going to be 100 minus 50, so 50 newtons. And this one is going to be 100 minus 100, so that equals 0 newtons. And this one is known as terminal velocity. Because if I was to say if this was every 10 seconds of it falling, so 10 seconds, 20 seconds, 30 seconds, 40 seconds. If I was then to look at 50 seconds, it would look exactly the same. It won't have changed, so Fr will still equal 0 and the velocity will still be at the terminal velocity. It doesn't change. Then if I looked an hour later, it would still be at the terminal velocity. If I looked 5 days later, it would still be at the terminal velocity. It's not going to change because it's reached its maximum and the two are now balanced until it lands. Okay, so the key thing here is you need to know that there are two factors that affect terminal velocity, and those two factors are, one is the speed and two is the surface area. Okay, and they're the two factors that affect air resistance. They're the two factors that affect air resistance. And then obviously terminal velocity's got a third factor, and the terminal velocity's third factor is going to be your weight. Okay, so but air resistance isn't affected by weight, only the speed and the surface area affect the air resistance. So what does that mean? Well, if I had a bigger ball with a bigger surface area but the same weight, my resistance will be greater. So let's say that was 50 and that was 100, and you've reached terminal velocity faster. And as you can see, each time we're getting faster, so the air resistance is getting bigger each time. So that's already taken that one into account. Now, the next thing that you need to do is you need to be able to plot this as a graph. Okay? So if I was to plot this as a graph, the way that I'd have to do that is, if I was to look at a distance time graph or a displacement time graph, what I've done is, we know that my ball is speeding up to start with until it gets to a constant speed. Okay, so that means that the gradient of this displacement time graph is going to be going until it reaches a constant speed. Okay, so let's say if you started 100 meters up, you'd then say that when that becomes a straight line, which is about there, you'd say that it reached terminal velocity at about 80 meters, roughly, because where it stops, where the gradient stops increasing, and then just continues at the same rate, that's terminal velocity is reached at 80 meters. And equally, you could say how long terminal velocity took to reach. We could say that terminal velocity took, let's say that was 10 seconds, and that's 20 seconds. You could say that terminal velocity took 15 seconds. After 15 seconds, it reached terminal velocity. Now that would be if you put it on a distance time graph, but you can also do it on a velocity time graph. So what we're going to say is that the velocity is increasing until it reaches a steady, until it reaches a constant velocity, and that velocity is known as the terminal velocity. So we know that if you're going to reach a terminal velocity where your velocity is not changing, the first thing that I find is that it's easiest if you just pop your line on there, okay? So you know that when it goes flat, that is your terminal velocity, okay? And how does it get there? Well, is the gradient going to be getting less steep, or is the gradient going to be getting more steep? And the clue is in this bit here, okay? So you know that to start with, your rate of change of velocity is going to be really quick, because you've got your maximum acceleration at the start, because you've got the biggest resultant force at the start, because the air resistance is the lowest at the start, which means that your gradient needs to be the steepest at the start, and then it will curve to v in 0, okay? And that we know from the previous example, we said that was at 15 seconds previously, but that's just a number just so that you can say so. So what you'd say is that from 0 to 15 seconds, the speed is increasing. So you can see that the velocity is increasing because it's always going up. It's just how fast it's going up is getting less until it reaches its terminal velocity. That's terminal velocity here. And if you wanted to work out what the terminal velocity was from this one, all you'd have to do is do the gradient. So you'd just do 80 divided by 5. So the terminal velocity for this one would be 80 divided by 5, which is 16. Meters per second. Terminal velocity, which means that this bit here would be 16 meters per second. And it would stay at 16 meters per second. So that's two graphs, the two different ways of looking at it. Okay, and the way that they tend to quite often ask this question is they tend to ask you about to describe the forces and the speed of an object based on the graph. So here you would say that the velocity is increasing because it is curved, but the rate of increase is getting less. So you could say that the rate of acceleration is getting less. And then you say until it reaches a constant speed, and you say that whilst the speed is increasing, it has a resultant force acting on it, because you know that if you're accelerating, you must have a force because you've definitely got mass. And in this example here, because it's falling, you'd say that the weight is greater than the air resistance. And then here, you'd say that the weight is exactly the same as the air resistance because it's no longer accelerating; it's now got a constant speed. And you describe that as terminal velocity, dv. Okay. Let's do one more example. Let's do an example of a parachutist, because then you can see how it's changing over time. So if you've got somebody who jumps out of a plane, and then a little bit later on they are in free fall, and then a little bit later on still they open up their parachute and then they land. Okay, and you want to draw the distance, time and velocity time graphs off that, so let's do the velocity time graph first this time. And so you'd say that to start with, you've got a very rapid increase in velocity. So that's going to be there. Okay, and this bit here to here, that's the terminal velocity, whatever that might be. And this bit is all the time is accelerating, whilst his air resistance is less than his weight. But here his air resistance now equals his weight. So then he free falls under, just here like this, just falling like the parachute's opening. Then he opens up the parachute. He has a massive increase in his surface area, which massively increases his air resistance. Okay, And that pretty much, because that's so sudden, that'd be really fast, okay? It wouldn't be exactly like that, but it might be like that, for example. Okay? But it'd be really, really fast where he opens his parachute. And now here, he's now got a terminal velocity with parachute. Okay? And the reason for that, the reason why his velocity went down here, is because if you imagine that you were falling really fast, and then you increased your surface area by a large amount, you're going to have a really large air resistance. And this is the only time when air resistance is bigger than weight, is when you are already falling very quickly and you open up the parachute, which increases your surface area, which makes you slow down. So so then he goes like that, and then it's a terminal velocity, and then when he hits the ground, it stops pretty much straight away. So that would be your with parachute kind of example. But these drops here, that's because the air resistance is bigger than the weight, otherwise the velocity never decreases. So on this example here, where I didn't open up the parachute and my surface area didn't change, the velocity goes to a maximum and then stays at a maximum until it hits the ground. On this one, because I changed my surface area, my air resistance actually increased. The other thing that can do that is if you change the substance. So for example, let's say that this was a diver jumping off a diving board, and in air he reaches terminal velocity, and then he hits the water, and then he slows down because the water resistance is far greater than the air resistance, and then he goes at and then he carries on sinking at a new terminal velocity in water, but that is lower until he hits the ocean floor or whatever it might be. Okay, so the only times where air resistance will be greater is either if you've fallen into something different like a liquid, or if you change the surface area with something like a parachute.